So this is exam 4 review on exponential and logarithmic functions, and we're going to start by using our calculator to approximate the value of each expression to 3 decimal places. So let's take out our calculator and let's do this first one. So we just hit log of 3 in parentheses, and we get out 0.477 since the 4th decimal place is a 1. Our answer is just 0.477, so this is approximately 0.477, and then we need to do ln of 213. So here's the ln button, and we hit 213 in parentheses and then enter, and we get out 5.361. Since the 4th decimal place is a 2, we just drop it off and we get 5.361. So this is approximately 5.361. Let's check. So yeah, 361. All right, and then the last problem, we want to do log base 5 of 32. Now this one's a little bit of a problem because you don't have a log base 5 on your calculator. So what we can do here is we can change it into ln's or logs. Let's just do ln. So it's just ln of 32 over ln of 5, which is approximately, and this is actually equal to, so this is an identity. All right, so this is equal to that, and then it's going to be approximately, we'll use our calculator here, and we'll have ln of 32 in parentheses divided by ln of 5 in parentheses, and we can hit enter, and it'll spit out our answer of 2.153. So 2.153. Let's check it just to make sure. So that looks good. Another thing you can do. Let's see if I can find this on here. There is actually a log base button. If you hit so I've never done this before, but I saw it a few days ago. So if you hit alpha y equals and you hit over, there is a log base button. So let's see if we can't get that to work. So I hit number 5. Oh, and it actually does it. Oh, so that's nice. So you hit 5 and hit over and hit 32. All right. The point of this problem is just to make sure you can calculate logs at different bases with your calculator. And remember what this number actually means. So this 2.153 is a number you raise 5 to get 32. So you can always check this with your calculator. 5 raised to that answer should give me 32. And that's what the log says basically. Okay, let's move on to the next problem. And so on this problem, we want to use the properties of logarithms to solve the problem. So you have two problems, A and B. One, you're going to condense the expression. The other one, you're going to expand. And we're going to use these rules of logarithms. Let's write them down over here so we have them all written down. So there's the fact when you add logs, you multiply on the inside. So m times n, versus when you subtract logs, you divide on the inside. So m divided by n. And then the final one is a power rule. So you have a product rule, quotient rule, and then you have this power rule. It works with powers. So log base b of m to power p, the p can come down in front. So the power comes down in front. So log base b of m. So these are sometimes referred to as the log laws, or just the rules of logarithms. And we're going to use these 3 rules to write this as a single logarithmic expression. So this is going to be equal to, there's all kinds of things you can do. You can kind of see you're going to do here. When you subtract, you divide. When you add, you multiply. But first, we have to get rid of these powers, or rid of these products here, and turn them into powers. So I'm going to use rule 3, which allows me to take this 2 and put it up in the exponent of x. This is the same as ln of x squared minus ln of y to the 1/2, and then plus ln of z cubed. And so you can just take these powers here, so these products, right, 2 times 2 times 1/2 times 3, and write them right up into the powers. That's just by rule 3. Okay, and then you have a couple choices here. You do need to be careful because the order does matter. So always make sure you work left to right. So what you have here is ln of this minus ln of that, which has this form. And so we're going to divide on the inside. So this is ln of x squared divided by y to the 1/2. And then we still have plus ln of z squared, or z cubed, sorry. All right, then finally, we're going to apply this first rule. Since we're ln of this plus ln of that, then we'll multiply this and that on the inside. So that's equal to ln of x squared z cubed divided by y to the 1/2. And you can leave it like that, or if you want to, you can take care of that fractional power and rewrite it as ln of, we have x squared z cubed, and then instead of writing it to the 1/2, we'll write the square root of y. And that can be my final answer. Either one is good. I don't really care which one you give me. As long as you apply these rules in the correct order, you'll be just fine. Okay, so that's condensing a logarithmic expression. And now here, we want to expand the logarithmic expression. All right, so let's do that. So the first task is to try to figure out which rule are you going to use. I mean, you obviously have a power here. You're obviously multiplying here, and then you're dividing there. So you could use one of the 3 rules, but which one? You can use all 3 of the rules, but which one do you apply first? And you always apply the rule that involves everything. So if you think it's multiplication, you'll notice multiplication just involves this thing and that thing, but not the bottom thing. So that'd be wrong. The division, though, involves everything. So it has a top and a bottom, and so this is the first rule we're going to apply. And so we have log of this divided by log of that. So it's going to be equal to log of this, so 3x squared z, minus log of that, so log of y. And then the next thing we're going to do, we can't take it to the power yet because we don't have something to a power. We have something times something to a power times something else. So we need to get rid of that. So let's take a look at this as multiplication. So we have log of this times that. And so we can use this first rule going the other way, right? Because you have this times that. So we're going to go this way. And rewrite it as log of 3x squared plus log of z minus log of y. All right, so that's good. And then for the same reason as last time, we still can't use this power rule because you have 3 times x squared. You need to just have something to a power. But 3 times, we can use that same rule, rule number 1, again. Because again, you have this times that, so you have 3 times x squared. So that's the same as log of 3 plus log of x squared plus log of z minus log of y. And we're almost done. We can finally use this power rule right here to bring down that 2. And so that'll equal log of 3 plus 2 log of x plus log of z minus log of y. All done. And so that's our final answer right there. Let's take a look at our next problem, in which we're solving exponential and logarithmic equations here. So let's solve this first one for x. So this is an exponential equation because you have x in the exponent. And in order to solve this, you know you're going to need to use ln's, but we'll wait until we have this term by itself. So first we'll add 15 to both sides. And we'll get 9 times 7 to the 2x equal to 18. We'll divide out by the 9. And so my goal is to get this 7 to the 2x by itself, and then I can ln it. And so when I divide out by 9, I get 7 to the 2x equal to 2. Now I can take out my ln tool, my ln function, which undoes exponents. And you can use any log, but we always just use ln's to try to get more comfortable with them. But you can use log-based head, you can use log-based anything, really. And then this 2x, it's really that third property we talked about before, comes down in front. And so we get 2x ln of 7 equal to ln of 2. And then we can divide out by the 2 in ln of 7. So here, if you divide out by 2, 2's cancel. And if you divide out by ln of 7, the ln of 7's will cancel. And you need to do that to both sides to make sure the equation remains balanced. And then we get our answer, x equal 2 on the left, because all this stuff cancels. And you get ln of 2 divided by 2 ln of 7. We can approximate that on our calculator if we want to. So we can take ln of 2 in parentheses and then divide it by left parenthesis 2 ln of 7 in parentheses, and hit enter, and we get our answer. Remember, you have to put an extra set of parentheses around that. And so here we get 0.178. Let's do the 3 decimal places. So approximately 0.178 is our answer. Remember, you can check your answer by simply plugging this back into the problem. So you can do 9 times 7 raised to the 2 times second answer, so 2 second answer, and then hit down minus 15. If you get out 3, we know we did it right. If you didn't, then we may have made a mistake somewhere, and you may need to go back and find it. But remember, don't erase your work on the exam, because I can give you partial credit. Another thing I'll point out that I saw a few days ago is that there is a button. If you hit alpha y equals, if you have a newer calculator, and hit enter on number 1, it does put it in this nice fraction form for you. So if you have a tendency to forget parentheses, the newer calculators do have this ability to write it in this form, so you don't have to remember those parentheses. Now, whether that's a good thing or a bad thing, I'll leave it up to you, because it's just remembering an extra set of parentheses, which is just really order of operations. But you can avoid that if you have a newer calculator. Okay. Let's get off of here, and let's go down to part B, which is solving a logarithmic equation. All right, so solving a logarithmic equation, and this one in particular, you're going to use those 3 properties again. So the first thing you want to do is rewrite this as a single logarithm, and then you'll have log of this equals log of that, and so you can drop off the logarithms and just have this equal that. So let's just do this. So before I divide on the inside, I have to get rid of that 2. So I need to write that up in the exponent. That's by that third property, remember. So I have ln of x plus 8 minus ln of x plus 2 squared equal to ln of 1 over x minus 1. And then because I'm subtracting in here, I can divide on the inside. So I have ln of x plus 8 divided by x plus 2 quantity squared is equal to ln of 1 over x minus 1. And now I have ln of this equal to ln of that. And because the ln function is 1 to 1, I know the insides have to be the same. So this has to be the same as that. So I can set them equal to each other. So I really have x plus 8 divided by x plus 2 quantity squared equal to 1 over x minus 1. Now this is a rational equation, and to solve a rational equation you need a clear denominator. So what I'm going to do is multiply both sides by x plus 2 squared, because that'll clear the denominator on the left, and also times x minus 1, because that'll clear the denominator on the right. So when you take this times that, these two things cancel, and you just get x plus 8 times x minus 1 on the left equal to, and then on the right, these two things cancel, so you just get x plus 2 quantity squared on the right. And then we're going to multiply these things out. So what I have now is really a quadratic equation. So I went from a logarithmic to a rational to a quadratic equation. So when you FOIL this out, so just use these arrows and multiply everything together, and you're going to get x squared plus 8x minus x, so that's plus 7x, and then minus an 8. is equal to, and then multiply this out, so x plus 2 squared, remember x plus 2 squared, it's x plus 2 quantity times x plus 2, not x squared plus 4. There's always this middle term here, so it's really x squared, you have the middle term 4x, then plus 4. And then what's nice about this quadratic equation is as soon as you take off the x squareds on both sides, they're going to cancel, and you're going to get 7x on the left, 7x minus 8 on the left, equal to 4x plus 4 on the right. So now you have a linear equation. Let's add 8 to both sides. And so we get 7x is equal to 4x plus 12. And then let's take away 4x from both sides. And so we get 3x on the left and 12 on the right. Divide both sides by 3, and x will be equal to 4. Now let's check our answer just to make sure, because it's easy to make mistakes here. So to check our answer, all we need to do is plug 4 back into our original equation. So since it's an ln, we have that button. So we have ln of 4 plus 8, in parentheses, minus 2 ln of 4 plus 2. And then we'll hit enter, and it spits out this number, negative 1.09, blah, 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 blah. All right, so then we need to check the left-hand side, so ln of 1 divided by, and then ensure you put parentheses around the bottom. So left parenthesis 4 minus 1 in parenthesis, enter. And we get out the same number on the right-hand side, so I know I did this right. So oftentimes, if you would have seen one of my exams when I was taking a class like college algebra, you see a check by that, or sometimes I even cross off the problem because it's like a check through the problem because it's like I know that's right, and I even checked it. And so I know that I did it right. Okay, so moving on, we have number 4. And so on number 4, we want to find a formula for the table. Now notice it doesn't tell us which type of formula to find. You probably know it's exponential, but on a final you may not know, so you'll have to test the data to see which is which. And so you'll notice if you try to subtract these outputs, you don't get the same number each time. So 256 minus 1024 is one number, whereas 1024 minus 4096 is another number. So it's not linear. But if you take the outputs and you divide them, always the final minus the initial. If you take 256 and then divide it by 1024, you're going to get a number that's 0.25. So let's write this down so you can see what I'm doing. What I'm going to do, I'm going to take pairs of numbers and I'm going to divide them. So like 256 divided by 1024. So instead of subtracting them like you would do for linear data, you divide, because that's what exponential data really is, and you get 0.25. And I bet if you take 1024, always final, and then divided by the initial, I bet you also get out 0.25. And so let's check that one out. So 1024. And after that, you're pretty much guaranteed, the way the problems are constructed, that that's what's going to happen each one. Oh, 0.25. And so I would guess if you take 4096 divided by 16,384, you also get out 0.25, and this is also a 0.25. So each time, right, to move to the next number, to go from this number to that number, you're going to take times 0.25. To go from 16,384 to 4,094 times 0.25, and so on, and so on. And so you can see the formula for this thing, my g of x, since the output is g of x, is equal to, you can have some starting value, which remember, the starting value always happens when you plug in 0. So that's at 1024. And you're going to multiply by, so you times 0.25. And so that idea is you raise it to the x. Right? Not times x, but raise to the x, and you're multiplying by it each time. And so there's the formula. And you can see that it models this. You can even check it with your calculator. So suppose if you plug in -2, you should get out 16,384. So let's check it. 1024 times 0.25 raised to the -2. And we do get out 16,384. So it checks, and so I know it's right. So this is my formula. Right. Another way to do this is just to set up the form and use data points. So if you don't want to be as intuitive as I was here, you can actually just write down this is going to be an exponential c times a to the x, and you can plug in 0. and you get out 1024, so you'd have c times a to the 0 is equal to 1024, and you could use the 1 and you get out 256. So if you plug in 1, you get out 256. And you'll see here a to the 0 is 1, so it immediately tells you that c is 1024. And so here I have 1024 times a is equal to 256. And of course, if you solve this for a, then you wind up with a equaling 256 over 1024, which is just equal to 0.25, or 1/4, however you want to write it. So this is an example of exponential decay. And this is just another way to do the problem. And we're going to do this again on this type. So they give us a little bit different information. They give it to us in functional notation. So we're going to find f of x, or let f of x be an exponential function with f of -1 equal to 10 and f of 2 equal to 80. Find a formula for f of x. So really, it's the same type of problem. You have x input and you have output f of x. So if you plug in -1, you get out 10. If you plug in 2, you get out 80. We know the form. It's an exponential function, so it looks like this, c times a to the x. And we know if you plug in -1, so a to the -1, you get out 10. Versus if you plug in 2, so c times a squared, you get out 80. And we just need to solve for c and a here. Now remember, if it's negative, you put it in the bottom. So this is really c divided by a is equal to 10. So we can simply solve this for c by moving over a, so multiply both sides by a, so you get c equal to 10 times a. And then you can use this information, since you know c is 10 times a, wherever you see a c, you can replace it with 10 times a. So you have 10 times a, and then times a squared equals 80. And so then you have 10 times a cubed is equal to 80. And you divide out by the 10, so you get a cubed equal to 8. And then to undo a cube, you take the cube root, so you raise both sides to the 1/3 basically. So if you raise the left to the 1/3, 3's cancel, and you get 8 to the 1/3, which is the cube root of 8, which is equal to 2. And so if a is equal to 2, you can come back here and say c is equal to 10 times 2, which is equal to 20. And basically I have c and a, so I can write down my formula. F of x is equal to 20, that's my c, and then times 2 to the x. And you can check your answer by plugging in the numbers. Like if you plug in 2, that's 20 times 2 squared, which is 20 times 4, which is 80. If you plug in -1, remember 2 to the -1 is really 1/2, and 1/2 of 20 is 10. So it checks. Right? This checks. So that's my answer for this problem. Let's look at the next one. So on number 6, we're solving some word problems here. And they're pretty easy to do once you kind of get the feel for it. So on this one, what do we have? We have a company's profits were $2.1 million in 1995. Since then, their profits have increased, so they're going to grow by a steady rate of 3.5% a year. What were the company's profits in 2003? Right, so there are a couple ways to do this. You can come up with a profit formula, so P of t, which is just equal to the initial value, which is 2.1, and then times the growth factor. So how is it growing each year? Since it's growing, you always have this 1 here that stands for the whole part, and then 3.5% is 0.35 as a decimal, and we'll raise that to the t. So there's a formula for that. And then 2003, well, it starts in 1995, so t is 8. So basically, this is saying, hey, find p of 8. And so this is equal to 2.1 times 1.035 to the 8. Of course, you'll need a calculator for this. So we take out our calculator, 2.1 times 1.035 raised to the 8. And out comes your number. Let's round this to, let's do it to 2 decimal places. So since the third decimal place is a 5, that becomes a 7, so 2.77. And remember, that's not just dollars, right? So it's approximately 2.77. And that's not just dollars, that's millions, right? $1 million. So that's important. The units are important. So when you write down 2.77, you don't think it's $2.77. It's actually about 2,770,000 Right, but we'll just write $2.77 million. All right, so that's an example of doing growth, and of course then below it we have an example with decay. So a hedge fund was valued at $20.5 million in 2005. Since then the value has decreased by 5% per year. What was the value of the hedge fund, or what is the value of the hedge fund today? Okay, so let's find a formula for the hedge fund. Let's use H for hedge fund, and it's be a function of time t. The initial value is 20.5, so we write down 20.5, and then times. Now here you're not going to start with a 1. Remember, the 1 is the whole part, so since it's decreasing, you have a 0 here because it's going to go down. It's going to be less than 1. And if it decreases by 5% per year, that means what you have left is 95%, so we multiply by 0.95. Notice it's not 0.05. If you multiply by 0.05, you lost a lot more than 5%. You actually lost 95%. So that's why we put 0.95 here. This represents a loss of 5%, and that's to the t. And then hedge fund today, so not today, let's say this is what, 2016 right now? So 2016 minus 2005 is what, 11 years? So t is equal to 11, right? 5 gets me to 10, 6 gives me 16, so yeah, 11. So it's saying find h of 11, basically. And so that's equal to 20.5, 0.95 to the 11th power, which is approximately, we'll need a calculator. So we take 20.5 times 0.95 raised to the 11th, which equals about $11.66 million. So you lost almost half of it there. So approximately $11.66 million. So there's my answer for that one. Okay, moving on to number 7. So number 7, we're going to start working with some logarithmic functions. We're leaving exponential functions for a while, and we're going to work on logarithmic functions. So the first thing we want to talk about is how do we find the domain? So remember, the domain of a function are just the numbers you can put into a function. And so there are basically 3 things that limit our domain when we're working with formulas like we've been. And one is very common, right? You can't divide by 0. So if it has a denominator, you need to watch out by dividing by 0. So you can see here this does have a denominator, so you could immediately say x can't be 1. And then you also need to watch out for square roots, and it's really an even root, but we work mostly with square roots. So you have to make sure whatever's on the inside is bigger than or equal to 0, because we don't want to deal with imaginary numbers or complex numbers like square root of -1. We want our numbers to be real. And so then 3 is the new one. If you have a logarithmic function, which I'm just going to write ln, you have to make sure on the inside this is always bigger than 0. And this is because you can't take the log of a negative number or 0. You can check this on your calculator. Like if you try to take ln of 0, it's going to say error, right? Error, domain, okay? You take get down and go to, and it'll tell you that the 0 is the problem. Or if you try to take ln of a negative number like -5, it'll say the same thing. It'll say error, right? It can't do it, right? So error, non-real answers, right? Which means you can't take the logarithm of a negative number and get back a real number, basically. Okay, so let's look at this problem. And yes, it does have a denominator, but actually if you work with this, this will take care of all cases. So we need to make sure that this expression is always bigger than 0. So for whatever x value you plug in, make sure it's bigger than 0. So write down 2x minus 10 over x minus 1. We always want this to be bigger than 0. And the way we find this is we do a sign diagram. Okay, so we're going to do a sign diagram. And a sign diagram is a pretty easy thing. When you're working with a rational expression, you just have to watch out when the top and bottom are equal to 0. Those are your sort of points you want to put on your number line. So you want to watch out when 2x minus 10 is equal to 0, and also when x minus 1 is equal to 0. So when 2x minus 10 is equal to 0, if you solve for this, you get 2x equal to 10, and so x is equal to 5. So we'll have x equal 5 on our number line, and then we'll add 1 to both sides, and we get x equal 1, so we'll also have x equal 1. And so the idea is if you plug in 1 to this, you actually get a vertical asymptote, right, to this expression. But when you plug in 5, you get out 0. So these are points where you can change, this expression can change in sign. And then you just test points to the left, to the right, and so on. And so let's take some test points. So I'll take a test point to the left, like 0's to the left, and 2's in between 1 and 5, and 6 is to the right of 5. Now notice I don't put them on my number line because that'll get me into some trouble. But I want to plug them back into this expression to see if they're positive or negative. And that'll tell me the sign of that expression in those regions. So if you plug in 0 here, you get 10 times 0 minus 10 divided by 0 minus 1. So really negative 10 over negative 1, which is positive 10, so it's positive, so that's good. It's positive there. If you plug in 2 to this expression, you get 2 times 2 minus 10 over 2 minus 1. Now on top, that's negative 6. On bottom, it's positive 1, so that expression is now negative when you plug in 2. So the values of that expression must be negative between 1 and 5. And then if you plug in 6, you get 2 times 6 minus 10 divided by 6 minus 1, which is 12 minus 10, which is 2, divided by 5. 2 over 5 is positive, so you're positive in that region there. So this tells me exactly what my domain will be. So I want to make sure this is bigger than 0, so that's when you're positive. So it's all this stuff up to 1. Don't include 1, because when you plug in 1, you actually get it to be undefined. And then from 5, but don't include 5, because you plug in 5, that's actually 0. But everything to the right then. And so my domain D would equal negative infinity to 1 union 5 to infinity. And that's my answer for that part. If we look below this, we have find the x and y intercepts if they exist. And so what we need to do on this one is remember what an x-intercept and a y-intercept is. So let's do x-intercepts first. So for an x-intercept, I just simply draw the xy axis, and I think about what does it mean to be an x-intercept. And of course, that's where you cross the x-axis. So I don't know where I cross it. So I don't know what the input value is, but I know the output value is 0. So what that means is you set the output equal to 0 to find that question mark. So we're going to take 0 and set it equal to that output. So the formula log of 2x minus 10 all divided by here x minus 1. And so basically we want to solve this logarithmic equation. Now the way we do this, remember, is we do what the log says. So there's a little 10 down here, and it says 10 to this is that. So this says that 10 to the 0 is equal to 2x minus 10 over x minus 1. Right, this is doing what the log says. So remember, if you have log base b of x equal to y, it's defined, the definition of this, what this says, what it actually means is b to the y is equal to x. Right, so that's one of the most important definitions when using logarithms. I always think about this too in terms of arrows, like b to the y is equal to x. All right, so now 10 to the 0 is 1, so we really have 1 equal to 2x minus 10 over x minus 1. This is a rational equation, so to solve it, we clear denominators. So I'll multiply everything by x minus 1. And so when you multiply this side by x minus 1, you just get back x minus 1. And when you multiply this side by x minus 1, the x minus 1's cancel, and you get 2x minus 10. So now we have a linear equation. And so what we'll do is we'll add 10 to both sides. And we'll get x plus 9 on the left equal to 2x on the right. And then we'll subtract x from both sides. And we just get 9 equal to x. All right, so that's my x-intercept. We should probably write it as a point. So that would be the point 9, comma 0. And that's my x-intercept. Now for the y-intercept, it's actually a lot easier. So let's draw the picture so you can see what you do. So the same thing, we can just use this picture up here. So y-intercept goes through the y-axis. Now on this one, I know the input is 0, but I don't know the output. So when the input is 0, you can just plug 0 in for x. And so for the y-intercept, we just find f of 0, which equals what? So you have log of, and wherever you see an x, you put a 0. So 2 times 0 minus 10 over 0 minus 1, which equals what? You have log of negative 10 over negative 1, which is equal to log of 10. And if you put this in your calculator, of course you're going to get back the number 1, because log base b of b to the anything, so log base 10 of 10 to the 1, is 1. All right, so I have 1 here. So I can write down my y-intercept if I want to. So my y-intercept would be input 0, output 1. So input 0, output 1. And that's my y-intercept. All right, so that finishes off that problem. Let's look at the next one. So we're back to working with some exponentials, but our exponential is the natural exponential, so that's e. So remember, e is a number, 2.718, that goes on forever. You can see it on your calculator if you want. You can just hit second ln and put a 1 there, and you see that's actually e right there. And it's used to model, growth or decay. And so in this one, we have a formula p of t equals 200 e to the 0.33t, and it models a population of a particular city in thousands, t years after 1998. Okay, so that's some important information there, so you might want to underline certain parts, especially the in thousands and t after 1998. And we want to find the population in 2007. So this is an example where they give us the formula, so we don't have to find it. They give it to us, and then we need to use it to do something. So typically, remember, these are input-output questions. So the first one's really an input question where they give us the input. And so t is equal to, if you start in 1998, I add 2 to get to 2000 and plus 7 to get to 2007, so t is 9. And then I do p of 9, and it's just a plug and chug. So I have 200 e to the 0.033, then times 9. I'm probably going to have to round this, so it's going to be approximately, and I definitely need a calculator, so 200. And then second ln to get to the e to the, and then 0.33 times 9. And you hit enter, and oops, I plugged that in wrong. That's your second entry. That's supposed to be another 0 there. Missed that one, 0. So second insert, put a 0, and now I get the right answer of about 269.16 blah blah blah, and that's thousands. So let's just round to the nearest thousand, so 269,000 people. So 269,000 people, approximately. Okay. All right, so what else? What's next? Now, that was an input question. The next one is probably going to be an output question. So determine the year that the population will reach 227,000. So now that's output stuff. So what I'm going to do here is take 227 and set it equal to 200 e to the 0.033 t. Now this one, you can either use technology, because it doesn't explicitly say you have to solve by hand. So if it says I can use technology, you can, and on the exam, it certainly would say whether you can or not. So you can graph the left, graph the right, intersect. I'm going to do it by hand because that's probably the harder way to do it, and the way that most people struggle with it. So I want to solve for t. So notice t is in the exponent. So eventually I'll have to ln both sides to undo the exponent and get the t to come down. But we can't do that till we get rid of the 200. So I'm going to divide both sides by 200. And so I get 227 divided by 200 equal to e to the 0.33t. And there's a 0 there, so 0.033t. And now you'll notice I can ln both sides because I have something to a power. So when I ln both sides, so ln of 227 divided by 200 is equal to, and sometimes we'll put this in parentheses so it's real clear it's ln of all that, is equal to ln of e to the 0.033t. And now that exponent can come down in front, so this exponent here can travel down in front. That's that property of logarithms, that third property. And so what we get is ln of 227 divided by 200 in parentheses is equal to 0.033 t, and then ln of e. Now what's nice about this is if you put ln of e in your calculator, you'll notice that ln of e is 1. And this always happens because it's basically this idea of log base b of b to the 1, if b is just 1. Right, there's a 1 here, but it's log base b of b to the anything is the anything, really. So remember, ln is really base e, so there's really an e down here, so that's why you get back 1. Right? Remember, ln is log base e, right, of e. Right, there's 1. Right, so it's following from this sort of identity, but it goes away, and so what are we left with? We're left with the ln of 227 over 200 is equal to 0.033t. 33t. And then we divide out by 0.033 on each side, so the equation remains balanced. And we get our final answer, so these cancel here. Let's do it in red. So this will cancel with that on there. And so you'll be left with t on the right. Let's just write on the left. So t will be equal to ln of what? So t will be equal to ln of 227 divided by, that's a 7 there, 200. And that's all inside the ln function. And then all divided by 0.033. So that's actually my answer. But if you want, and that's years, right? But if you want, I can approximate this. Right? But you have to have the exact answer there, but I can approximate it. Right? So what can I approximate it to? Let's see, I have ln of 227 divided by 200 in parentheses divided by 0.033. And so that's about 3.8 years. So if you want, you could write down about, so approximately 3.8 years. Right, that's fine. After you found the exact answer, you can approximate it. And then it's really determined the year. So really you would add what? Well, we began in 1998. So if you add 1998 to this would be in, and you can do this on a calculator if you want to add 1998. If you don't want to do it in your head, it's really just plus 3 years. So it's just in 2001. So in 2001. Notice you typically don't round up, even though it's 0.8. You don't round up to 2002 because you're saying in what year. So it would occur in 2001 if it follows this model. But you have to have the exact answer. Right? You can approximate it later on and write down, in 2001, or just leave it as 3.8. I really don't mind, but the exact answer is important to make sure you can work with fractions in an efficient way. Okay, let's carry on. So we had A and B there, and then we have our last problem, which is number 9, which is working with a logarithmic formula. And so on this one, the reaction time R in seconds to respond to n choices can be modeled by this formula. R of n equals 0.17 plus 0.19 times ln of n. Okay, so this is another formula problem, and again, do input and output basically. So if you said right here, what is the reaction time for 10 choices? You have to figure out n. Is n reaction time or is n choices? Or, so what do you plug into basically? So here, you would plug in for R because R is reaction time and 10 is choice stuff. So you plug in for n. So this is basically saying crunch R of 10. And so that's going to be equal to 0.17 plus 0.19 ln of 10. And that's approximately, and so you take out your calculator, and we're going to crunch this. So 0.17 plus 0.19 ln of 10 in parentheses and enter. And so it's approximately, and let's round this to 2 decimal places, so let's say 0.61 seconds. So approximately 0.61 0.61, and it's in seconds. It says the reaction time R in seconds. So that's how long it takes to make 10 choices, about 0.61 seconds. And then below it, how many choices are there when the reaction time is 0.5 seconds? And so now that's output, so we'll set it equal to, so 0.5 is equal to 0.17 plus 0.19 ln of n. And we'll solve this for n. Now again, you can use technology, graph the right or graph the left, and intersect, but again, the harder way is to actually solve by hand. So I'm going to practice that, and on the exam, if it says use your calculator, you can use your calculator, but if it doesn't, if it says do this by hand, then make sure you do it by hand. And so on this one, we'll solve this by hand. So to solve it by hand, we have to subtract 0.17 from both sides. We want to get ln by itself, basically. And we do 0.5 minus 0.17, you get this to be 0.33 on the left, equal to 0.19 on the right, ln of n. And when you do the subtraction, you just take away a dime, basically 40 cents, and you take away 7 cents, and you have 33 cents. And then we need to get rid of the 0.19, so you divide both sides by 0.19. Do not round on your calculator, just leave it as 0.33 divided by, let's fix that a little bit, so 0.33 divided by 0.19 is equal to ln of n. And then we're going to do what the log says. So remember, there's a little e down here, and so we'll take e to this is equal to that. And so we have e to the 0.33 divided by 0.19 is equal to n. And we're basically done. So here, if we crunch this number on our calculator, we can say what n is. We'll round to the nearest number of choices, I guess. So second e to the, and we have 0.33 divided by 0.19. Enter. And so it's about 5.6 choices, so 5.7 choices. Let's round to the nearest number of choices. So n, well, let's round to one decimal place. That way we can practice rounding. So if the second decimal place is a 7, we round up and we get 5.7. So here, this is approximately 5.7 choices. If we round to the nearest choice, we probably would round it to 6. And let's make sure that you can read this here. So that's choices. All right, a little bit better. All right. So that's an input question above, and this is an output question below. You can check your answer, remember? The way you check your answer on this one is you'd want to do 0. You don't want to plug it back into here, so you do 0.17, and then plus 0.19, and take the ln of that answer, so second answer, in parentheses. And if we get back 0.5, we did it right, which we did. So I know it's even right, so I can just check this one off, because I know it's right. What else? Below this, oh, there's solve this function for n. So this is just sort of an extra little problem. So really, r of n, we can just write as r. So really what we have is r equals 0.17 plus 0.19 ln of n. Now we want to solve this for n. I dropped off the functional notation on the left because that gets a little bit confusing. Just wrote it as the output r. And so we want to solve this for n. So the idea is try to keep n still and move over everything else if we can. So let's do that. So you would subtract 0.17, and we sort of did this above when we solved the equation, really. So you subtract 0.17 from both sides. So r minus 0.17 is equal to 0.19 ln of n, and then we're going to divide out by the 0.19. Still trying to solve for that n, so 0.19, and we'll get r minus 0.17 all divided by 0.19 is equal to ln of n. And then remember, we're going to do what the log says. So this is where our students typically get stuck, because they're like, well, what do I do from here? Well, you just do what the log says. There's a little e down here we don't write, but it says e to this is that. So I know that e to the r minus 0.17 divided by 0.19, that's all in the exponent, is equal to n. And so we can rewrite this, if you want, as a function. So the number of choices is a function of the reaction time r, and that's equal to e to the r minus 0.17, and this is all in the exponent, and divided by 0.19. So that's a formula for the number of choices, and it depends upon the reaction time. So a formula for n in terms of r, basically. You could actually check this by checking n of, up here, we found that if n is 5.7, you basically get out 0.5, or if r is 0.5 seconds, you get out about 5.7 choices. So if you do n of 0.5 on your calculator, right, so check it on your calculator. So here we would do second ln to pull up the e to the, and we'd put a 0.5 in there. So left parenthesis 0.5 minus 0.17, end parenthesis divided by 0.19. And we better get out 5.7, which we do when we round it. So 5.679, blah, blah, blah. And so this checks. So I just checked it on my calculator. So this checks off. Right, so that's me just checking my work there. But that's the answer.